Yeah.
Okay, great. Okay, so first of all, thank you so much for the invite, and I'm really sorry for not showing up. I really wanted to come for the first time, and I really wanted to visit the Waterloo campus. But yeah, as Gautam mentioned, stuff happens. Okay, so I want to talk about composition for differential privacy. I know there are lots of papers, about composition on differential privacy, but what I'm going to talk about today is that basically, we are looking at composition from a very different angle. We want to design mechanisms which are optimal for large composition regimes. So when the number of composition is actually very, very high. So what we did, we basically developed a kind of a framework for designing a mechanism in this regime, in large composition regime, and then we call it Schrödinger's Cactus, and we will see in a minute why we came up with this kind of cheesy name. Okay, so it's actually a joint work with my colleague Flavio from Harvard, Oliver and Lalita from ASU, and Weil, a PhD student from Harvard, and Faye, a postdoc from ASU. So I have to make it very clear that this is a work in progress. So please stop me if there is anything clear, if you have any suggestion, if there is any feedback, comment, or anything. If you think anything is not clear or right, please stop me right away. Okay, so the outline of the talk is as follows. I want to begin by motivating this regime while we are looking at the large composition regime. And then after that, I will talk about very, very basic concentration results for a very important random variable, which is called privacy loss random variable, which is actually the heart of the key in differential privacy. And then I will introduce a new family of mechanism, which we call it Cactus mechanism. And then we argue that this family of mechanism are basically optimal in this regime, in the large composition regime. And then and after that, I will introduce another family of mechanism, which we call Schrödinger mechanism. And then we argue that this new family of mechanism will also be optimal if we add an extra assumption, which is about the sensitivity. If the sensitivity of the queries are small, then Schrödinger mechanism actually are optimal. And then I will finish the talk by a bunch of numerical experiment, which actually shows that Cactus and Schrödinger are better than a widely popular mechanism in the community, for example, Gaussian mechanism or Laplace. Okay, so now let's just jump to the first part, motivation and concentration. So the motivation actually is very simple. Why do we have to care about large composition regime? It's actually because differential privacy is now being increasingly applied and integrated into machine learning. And we all know that machine learning algorithms are always iterative, and then you have to iterate the algorithm for many, many times in order to have a decent accuracy level. So this is actually an example that I took from this paper, very famous paper by Abadi et al. So there are 3 plots here. They correspond to 3 privacy utility trade-off for 3 different kind of privacy level. So it's actually privacy accuracy trade-off for the training classifier on MNIST. Here the y-axis is accuracy, and this is also delta, which is actually a privacy parameter. And then the x-axis is epoch. And what is epoch? You can think of epoch as the number of iteration times the subsampling rate. So in this example, subsampling rate is 0.01. So when epoch, for example, is 10, that means the number of iteration is actually 1,000. So you have to multiply it by 100. So, and here, so the first plot is when the privacy is very strong because epsilon is 0.5. The second plot is exactly the same trade-off, but when epsilon is equal to 2, so the privacy is a little bit worse. And then the third one is when epsilon is equal to 8, so the privacy is actually very, very weak. So I will describe what epsilon and delta are in a minute, but what I want to say about this example is that in this example, for this privacy level, if you really want to have a decent level of accuracy, for example, you want the accuracy to be 0.9, then the number of epoch should be something like 8 or 9. That means that the number of iteration is something like 800 or 900 or very close to 1,000. So we are very well in the large composition regime. And then this phenomena is not just for classification or classifier on MNIST. This actually happens for almost any machine learning application. So the number of iterations should be very, very high. So this regime is actually very kind of valid regime for almost any private machine learning algorithm. So the goal of this talk is we want to design some privacy mechanism with favorable privacy utility trade-off in this particular regime, in the large composition regime. Okay, so now let me just define differential privacy. I know that you're all familiar with differential privacy, but let me just define it one more time. So suppose we have a data set containing information of a bunch of individuals, and then we are interested in some aggregate statistic. Okay, so this X is basically the aggregate statistic that we are interested about this data set. But we know that we cannot really publicly release this aggregate statistic because of many different attacks. What we do is basically we just pass this aggregate statistic through this privacy mechanism, which basically generates a random variable as the output. And the distribution of this random variable is py given x. Okay, so now let's consider a hypothetical situation where we construct a new data set where we basically just change one of the individual in the data set. So we changed this person to an arbitrary different person. And now we compute exactly the same aggregate statistic. Here it's going to be x prime, it's going to be different probably. And then again, we pass it through the same mechanism, and then we get this distribution as the output distribution of this mechanism. What differential privacy requires is that these two distributions should be very, very close. Why? Because if the adversary observes, the output of this mechanism, if the distribution are close, then the adversary cannot really distinguish this distribution from this distribution. And hence, the adversary cannot really tell this data set apart from the other data set. So in that case, this person, this individual actually has a very a plausible deniability. So that means that this individual can always deny that he was part of this data set. Okay, but in order to make this intuition more formal, we have to have a measure of distance between distribution. Okay, so the original definition of approximate differential privacy is actually is defined as follows. So we say that this mechanism py given x is epsilon delta dp if for any measurable set, for any interval a, the probability of this interval a under the first probability, under the first distribution should be very close to the probability of a under the second distribution, according to this kind of condition. Okay, and then we want this to hold for any pair of neighboring data set. So basically for any x and x prime. Okay, so we put actually this supremum here. And then here, this d is any distance metric. Okay, so because we are dealing with a neighboring data set, then this x and x prime should be kind of close to each other. And then this s is most of the time is called sensitivity of the aggregate statistic. Okay, so we already know the sensitivity. Okay, this is the assumption. We know s, we know the sensitivity. Okay, so this is actually the original definition, but we want to use another equivalent definition, which is based on privacy loss random variable. So let me define privacy loss random variable. So this is actually the setting that we had in the previous slide. We can look at the log likelihood ratio of the output distribution. So we can look at the log of the first distribution divided by the second distribution evaluated at this random variable y, which is basically a random variable distributed according to the first distribution. Okay, so this is actually the log likelihood ratio, but in the DP community, it's called privacy loss random variable. And this is actually at the heart of almost any variant of differential privacy. You can define, or you can come up with an equivalent expression for almost any variant of differential privacy in terms of the privacy loss random variable. Okay, so yeah, so it's called actually privacy loss random variable. So okay, so we had this definition. And using a very basic algebra, we can show that this double supremum definition for epsilon delta dp can be written in terms of this expectation. Okay, so the expectation that involves this privacy loss random variable, and then this plus here, this is actually the positive part of this term. So if this term happens to be negative, you just replace it with 0. Okay, so now instead of dealing with this double supremum definition, we have basically this formula, which is a little bit easier to deal with. Okay, so now let's just look at the composition, and let me describe the easiest, the simplest setting for the composition, which is actually the IID composition, or sometimes it's called the non-adaptive composition. Okay, so again we have some aggregate statistic, X, and then we pass it through this mechanism, and then we get this distribution. But suppose, for some strange reason, the adversary wants to know X. So what happens is that the adversary keep asking the same query, keep asking the same question. So what you end up doing is basically just passing the same aggregate statistic through n mechanism. Okay, so an n is the number of queries, the number of questions that you are being asked. So now we have n mechanism, and that means we are going to have n distribution. But the big assumption here is that we assume that all these mechanisms are independent. So what it means is that the distribution, the output distribution will be IID. Okay. So now let's just go to the hypothetical situation where we have the neighboring data set. We have now X prime, we have n mechanism, and then each mechanism generates one distribution. So that means in this case we are going to have n distribution, but they're all the same. They are IID. Okay. So because of this IID assumption, the privacy loss random variable for this composition setting is going to be the sum of the privacy loss random variable of each of these small mechanisms. Okay, and then this yi is basically the output distribution of, the output of each of these mechanisms. Okay, so what is very important is that because of that IID assumption that we had, now the privacy loss random variable will be actually the sum of a bunch of independent random variables. Okay.
That's just like, having a joint distribution in the numerator, and then you convert it to a product and you pull it out. Is that essentially?
Exactly right.
Okay,
yes.
Yeah.
Okay, so so this is actually the privacy loss random variable after n IID composition, the sum of bunch of IID random variables. And then this is the definition of the original definition of epsilon delta dp. And now what we can do, we can basically plug this definition of the composition into this definition, and then we just say that the composition is going to be epsilon delta dp. Okay, so what happened is that we can say that the n-fold composition, which means the composition after n number of mechanisms, of this mechanism py given x is epsilon delta dp if this expectation is smaller than delta for any pair of neighboring data set. Okay, so all I'm doing here is just plugging this new privacy loss random variable into the definition of the epsilon delta dp. Okay, so this is just definition. Okay, so we can say that the composition, the n-fold composition is epsilon delta dp if this thing happens. Okay, but now again, look at this. This is the sum of bunch of IID random variables. And we know from a stat 101 or probability 101 that when we are looking at the sum of bunch of random variables, they are going to concentrate around their means. Okay, so what we can say is that when we look at the average of this privacy loss random variable, then this average is going to converge to the expected value of the privacy loss random variable. And what is this expectation? The expectation is actually the KL-divergence, the KL-divergence between this distribution and this distribution. Okay, so what it means is that if n is large enough, if the number of composition is large enough, then this term here can be approximated very well by this term, where now instead of this privacy loss random variable, what we have is just the KL-divergence. Okay, so now we have actually kind of a nice procedure. What we can, okay, so before that, and then this function is actually a non-decreasing function of KL-divergence. So this function, if you look at this function, is actually a non-decreasing function. Okay, so what it means is that if you really want to minimize this term, you have to basically look at the minimizing KL-divergence. Okay, so now we have a very kind of nice procedure in order to compute the privacy guarantee of n-fold composition. We just compute the KL-divergence between the output distribution of the mechanism for any neighboring data set. So we compute this KL-divergence for any x and x prime. And then we just plug that KL-divergence into this formula. We take the supremum for any x and x prime satisfying this condition. And then we claim that this actually gives us a very good approximation for delta. Okay. The goal of this talk is we want to use this approximation for delta to design a mechanism which gives us the smallest possible delta when n is large enough. And then as you can see, just because this function is increasing, in order to minimize delta, all we have to do, we have to basically look at minimizing the KL divergence. So if I can design a mechanism which minimizes KL divergence, that actually leads to a smallest possible delta. And that will be the goal of this talk. We want to design a mechanism which minimizes this KL divergence. Okay. So there are lots of paper, in the community about the optimal DP mechanism, optimal privacy mechanism. In the literature, there are so many, but the common thread of all these papers is that they are designed for the single shot setting. There is no composition in the design procedure of all this mechanism. So what we are going to do in this talk is we want to assume that the number of composition is large enough, and then we want to design mechanism for that particular regime. So all these works, they are very interesting, but there is no composition in them. So this is actually how our work is different from them. So recently there is a very nice variant of differential privacy, which is called Gaussian DP. And so in this paper, they prove some sort of central limit theorem kind of result for the composition. It's a very interesting, but it's very close actually to what we are doing. But the difference is that there is no design mechanism. So what they are doing is that we know the small mechanism, and then we want to compute the composition. And again, it differs with us. It kind of different, from what we are doing in that we are designing a mechanism. So we have some sort of this kind of not CLT, but some sort of the concentration result. But we want to use that concentration result to design a mechanism. And then if you are doing information theory, I have to say something about this Gaussian DP. There is a very nice kind of connection between Gaussian DP and information theory. So all this central limit theorem that is proved, in this paper for Gaussian DP, they are essentially similar to the finite block length analysis of channel capacity in information theory. So if you are interested in information theory and differential privacy, this connection, I think it deserves to be looked at a little bit more. So there's a very nice kind of bridge between information theory and differential privacy. Okay, so with this introduction out of the way, now let me jump to the first part, the Cactus mechanism. But before that, is there any question? Okay. Okay, so this is the setting that we have. We have two distributions, py given x and py given x prime. And now we are looking at the KL divergence between these two distribution. And then as you may recall, the goal is we want to minimize this KL divergence because minimizing KL divergence leads to minimizing delta. Okay, so we are making two assumptions. The first assumption is that the output of this mechanism is an R-valued random variable. So the dimension is actually 1. And then the second assumption is that instead of having some metric D, we are looking at L1 distance. So we assume that the L1 distance between x and x prime is smaller than s. That's it.
Sorry, and to be clear, like you say, are we going to be looking at L1 distance for the inputs, or are we going to only look at one-dimensional inputs?
Yeah. So it's one dimensional. So the x and x prime, they are just a bunch of one-dimensional scalar.
I see. Okay. So for now, we're going to deal with everything in a 1D setting.
Absolutely. Yes. So yeah, I agree. So this assumption too is absolutely not restricted. This is actually the whole, all differential privacy. They assume this kind of sensitivity inequality, but this assumption one might be restricted, but it can be dropped. In the paper, we have something about, what if the dimension is not 1, but the whole analysis becomes ugly and super messy. Okay, so this is the goal. We want to minimize the KL divergence, and then the minimization is taken over this mechanism py given x. Okay, and then to be more precise, we are minimizing the worst case KL divergence, the maximum KL divergence. So we are looking at all possible x and x prime, which satisfy this. And then among all this family of x and x prime, we want to design a mechanism which minimize the worst KL divergence. Okay, So this is actually the goal. But there is no utility here. So without any utility constraint, this optimization is actually very, very trivial. Because if this mechanism makes y and x independent, then this distribution will be exactly the same. So the KL divergence becomes 0, which is the smallest possible value. So it actually minimizes. So we need some notion of utility. And the way that we define the utility is actually something like this. So we want to basically—
just to explain the previous thing you said, like essentially you're saying you can trivially satisfy this if you just have the output be independent of the input, right? Like
exactly. Yes. So yeah, so exactly because of this, we have to add some utility constraint into this optimization, otherwise the optimization becomes trivial. So we are looking at the distance between output and input of this mechanism as a metric of utility. Okay, so when the input is x, we are looking at the gap between y minus x, and then we want this gap on the average to be smaller than this constant c. And then this c here is just arbitrary cost function. Well, not arbitrary, the cost function should satisfy a bunch of properties. But for now, we can just consider, something like this, x to the alpha for any alpha. But any cost function satisfy, all this property, we can just basically just, our result holds.
So in particular, say just like the absolute value is something can we keep that in mind? Would that make it simple or?
Absolutely, yeah. So again, alpha is equal to 1. That gives you the absolute value, right? Absolutely. But again, for any alpha, you can have something like this.
Okay.
Okay, so this is the optimization problem that we want to solve. Okay, so the first result that we had was that the optimal mechanism is additive, and that means that what the mechanism does is that you just get the input and then add some noise to it. And then this noise, Z, comes from this distribution, which is absolutely continuous. Okay, so this result is absolutely not surprising. Exactly the same result was proved for the single shot setting. But what it implies in our setting is very, very important. So what we can do, we can use the structure of the optimal mechanism that comes from this result. And then we can use this structure to kind of simplify this optimization problem. Okay, what happens is that we can basically, so instead of looking at this KL divergence for any x and x prime, and then this kind of utility, what we can do, we can just look at the KL divergence between this noise distribution and its shifted version. So this TA is just the shift operator. And then this A is the size of your shift. And then the assumption is that the shift should be always smaller than the sensitivity. And then the utility measure is just the expected value of this C, and then that should be smaller than C. And then the expectation is with respect to the noise distribution. And we are minimizing over all possible absolutely continuous measure on R. Okay, so at least it makes the optimization problem a little bit more compact. So when you're looking at this optimization, it's very ugly. When you look at this is beautiful. It's very subjective, but this is actually much more compact. Okay, so again, this is very compact optimization, but the bad news about this optimization is that it is infinite dimensional optimization problem. So the chance that we can solve this, analytically solve this optimization, it's very slim. So we cannot really solve it. So that's what we conclude at the end. And what we did was basically just discretize this probability measure, and then we just try to solve the quantized version of this optimization. Okay, so again, we have this probability measure. We can quantize it. We can plug it into this definition, and then we hope that that quantization makes this optimization finite dimensional. Okay, so that was actually the hope. And then just piece of notation, let's call the value of this optimization KL star. Okay, so what we did, again, we quantized the additive noise distribution, and then we kind of explicitly parameterized the distribution just in a certain interval on the real line. It's a very kind of messy analysis, but you can see the paper for the detail. But this is actually the result. So we get a finite dimensional optimization problem, So here we have P. So this P is not probability measure, it's actually a PMF. So it's actually a probability vector on some finite dimensional set. And then instead of A is smaller than the sensitivity, we have this maximum over K, which is from 1 to N, and N is just some number like 1,000 or 2,000 or something. Okay, so this is actually the quantized version or discretized version of the our original optimization problem.
Okay, just to make sure I'm understanding, like there's going to be some algorithm, you feed in some stuff, and it gives you out a noise addition mechanism. Is that right?
Exactly correct. Exactly.
Can I ask, like, what exactly do you have to feed into this algorithm to get the output?
So there are a bunch of parameters here. So N and this big N and R. So there are 3 parameters in this algorithm.
Okay, like are they all like hyperparameters? Like, you know, the more you give them, then like.
So it's actually the quantization. So this is actually kind of like the parameter of any quantization that you have. So if this n means how fine you are quantizing your results. So n is like 2,000 or 3,000 should be fine enough.
Sure. Okay. So many of these are for quantization, but you also have to give in, say, the cost function as well as the bound on the cost function, right?
Absolutely. Yeah. So you're talking about this, right?
Yeah. Okay.
Yeah. So we are quantizing, that the utility measure as well, right?
Okay. Cool. I think I get it. Yep.
So what I know it is ugly, but what is important is that now we have a finite dimensional convex optimization problem, and it is actually solvable. You can just pick, your favorite convex optimizer, and then you can just use it, to solve this optimization. So we use interior point method. So we use this interior point method, and then this is actually what we get. So it converges very, very fast. So here we are using the 1,000 quantization point. So that capital N that we had in the previous slide is going to be like 1,000. So as you can see, it looks kind of like Cactus. So that's why we call this distribution Cactus distribution. Okay, so it's going to be the distribution of the noise that you're adding to your input, right? So this is the noise distribution, which we call it the Cactus distribution, and the corresponding additive mechanism, we call it the Cactus mechanism. Okay, so the result is that if you look at this quantized optimization problem, and then let's call the value as KL star Cactus. So we show that the value of this quantized optimization actually converges to KL star, which was actually the original optimization problem that we had. So if your quantization is good enough, then we have this convergence. So if for example n is like this big N is something like 1,000, you are not using too much. So basically, what that algorithm gives you, this is actually the optimal. So because of this result. Okay, so let's just look at this again. So this is again the noise distribution. So here, so this again, so the quantization point is something like 1,600. The other 2 parameter N and R are also given here. So here the cost function is quadratic, the sensitivity is 1, and then the utility constant is like 0.25. So if you look at this, what you can see is that this distribution is totally different from Gaussian, right? I mean, because if you remember, the Gaussian density is kind of monotonic, on the positive half, but this thing is not monotonic. So it just goes down and then comes up, and then there's a peak here, and then again goes down. There's a peak here. So it's definitely not monotonic. So it's very, very different from Gaussian.
And this is like not just an artifact of your quantization.
No. So okay. So very good point. So all these peaks here are happening exactly at the sensitivity. So sensitivity is 1. So we have peak at 1, and then 2, at 3, and then 4, and so on. So it's definitely not the artifact. So again, it looks very different from Gaussian. So now let's just compare this Cactus mechanism with the Gaussian mechanism to kind of confirm, what we see from this plot. Okay, so this is actually what we get. So the y-axis is the maximal KL-divergence. So remember the maximum of the KL-divergence, and then the x-axis is this utility constant C. And then we are looking at the quadratic cost. The blue curve is the Cactus distribution or Cactus mechanism, and the yellow or the orange is Gaussian. So as you can see, if C is small enough, which means the utility is very good, then there is a huge gap between Cactus and Gaussian. Okay, so for example, the KL for Cactus is here, but for Gaussian is something even bigger than 10. But then at some point, when you sacrifice your utility, when you increase C, at some point this two actually becomes kind of the same. So Cactus and Gaussian become the same when C increases. Okay, so this part, why Cactus is better than Gaussian, we understood, because we optimize the KL-divergence. So Cactus is the optimal, so there should be a gap. But this part was kind of buffering for us, and we couldn't really understand why Cactus and Gaussian should kind of converge to each other. And this is actually the subject of the second part of the talk. So we want to just zoom in this area and then see why we have this kind of convergence. And just to give you a spoiler, we can analyze this convergence using Schrödinger equation. So using Schrödinger operator basically.
How should we think of you're sort of dividing into these two regimes of lower C and larger C? Do you have any interpretation of what we should take from that?
Yes, exactly. So instead of dividing in terms of the lower C and bigger C, we would kind of divide it in terms of the big sensitivity and a small sensitivity, because they are equivalent. Very good question. Very good question. So I will talk about it maybe in a minute. Okay, so now we want to talk about this Schrödinger business, Schrödinger mechanism. And then what Schrödinger mechanism does is basically give you the optimal mechanism for a small sensitivity regime. Okay, so again, here we are kind of looking at a small c and big C, but instead of having this kind of difference between a small c and big C, we want to look at a small sensitivity and big sensitivity. And then I will talk about why they are equivalent. Okay, so this is the optimization problem that we had. And so now, this probability measure is actually absolutely continuous. So let me just write everything in terms of the PDF. Okay, so now we have this PDF here, we have this PDF, we have again, this KL-divergence between this PDF P and its shifted version, and now the cost function again is with respect to the noise PDF. And again, this C can be anything like x to the power alpha. But here, the assumption is that the sensitivity is very, very small. Okay, so now you may wonder why on earth, we should look at, this regime, why sensitivity should be very small. I have two answers for this. The first one is that there are a bunch of queries in practice whose sensitivity is actually very small. For example, if you look at the proportion of something in the data set, for example, the proportion of people in the data set having a certain property, then we can show that the sensitivity of this query is actually 1 over the size of the data set. So if the data set is large, then the sensitivity becomes something very, very small. So this condition, while it looks a little bit weird, it might happen in practice. And another reason is exactly about the question that Gautam asked. So we wanted actually to study this optimization problem when S is large enough. Okay, so what we can do, we can basically just replace this C. I mentioned S, I guess. Yeah, so we want to study this optimization when this C is large enough. Okay, so but what we can do, we can basically replace this C here with 1. And replace this S by S over C. So large C is kind of the same as a small sensitivity. Okay, so and then we kind of felt that maybe this category of a small sensitivity and big sensitivity might make more sense than big C and a small c. So yeah, so here we have now this assumption S goes to 0. And now with this assumption, we want to solve this optimization problem. Okay, so and then at the end of this part in a couple of minutes, you will see that why we have this kind of convergence here when C is big. Again, C big is equivalent to saying that S is a small. Okay, so when A is a small, when this shift parameter A is a small, then there is a very folklore result in information theory which says that the KL divergence is actually kind of the same as the Fisher information. Okay, so this IP is actually the Fisher information. Okay, so this is a very, very well-known result in information theory dating back to Kullback in 40s or 50s, I guess. Okay, so with this result, if you want to look at this optimization problem, what we have to do, we have to basically look at the minimizing the Fisher information. So instead of solving this optimization problem, we have to solve this optimization problem. So we are minimizing the Fisher information subject to this utility constraint. And then we call this, the optimal value, the optimal density, we call it PS star CC. And then we will see that this is actually a unique optimizing distribution. Okay, so by the end of this, maybe like in few minutes, you will see that solving this optimization problem is equivalent to finding a certain eigenfunction of the Schrödinger operator. Okay, so this is actually the result of this part of the paper. Okay, so the noise density that minimizes the Fisher information is actually a certain eigenfunction of the Schrödinger operator. But in order to make sense of this statement, I have to define what is this certain and what is the Schrödinger operator, because before this work I never heard about Schrödinger operator. So if you're like me, then I have to define what the Schrödinger operator is. Okay, so for any measurable function v, the Schrödinger operator hv with potential v is actually something like this. So you're looking at the second order derivative. The second, so minus y double prime is actually the second derivative plus v times y. Okay, so this differential equation is actually the Schrödinger operator with potential v. Okay, so if there exists some function y that solves this equation for some e, then we say that that function is the eigenfunction for this operator. Okay, so this function is called the eigenfunction of the operator if y is differentiable, y prime is absolutely continuous, and then there exists some constant e such that we have this equality. Okay, so this is exactly like the eigenvalue or eigen vector in matrix. Okay, and then so this actually just answer what this Schrödinger operator is, and then this certain. We will see that this certain means the smallest, so the eigenfunction corresponding to the smallest eigenvalue of this operator. Okay, so now we have the optimization and then the Schrödinger operator. So the potential that we have in this Schrödinger operator is actually comes from this cost function c multiplied by some constant theta. Okay, so the potential of the Schrödinger that we look at is basically theta times c. Okay, so the first result that we prove is that for any positive theta, there exists a unique unit L2 norm eigenfunction that we call it y theta c that is always positive and it's even, and the corresponding eigenvalue is the smallest eigenvalue of the Schrödinger operator. Okay, so there are two key words here. The first one is that unique unit L2 norm. So the unit L2 norm means, if you look at the square of this function, then it integrates to 1. So that means that, the square of this function, y theta c, the square of this function is actually a PDF. Okay, so that's actually the first keyword. The second one is that the eigenvalue corresponding to this function is actually the smallest eigenvalue of the Schrödinger operator. Okay, so now we can use these two properties to define Schrödinger mechanism. So Schrödinger mechanism is actually an additive mechanism. So the output of this mechanism is actually equal to x plus z, where now this noise has the PDF y squared theta c. Again, this is a valid PDF. And then it satisfies this equation, where this e is the smallest eigenvalue of the Schrödinger operator. Okay, so this equality actually comes exactly because of this result. Okay, so why we are looking at this Schrödinger mechanism? Because as you can guess, this Schrödinger mechanism is actually optimal. So it basically minimizes the Fisher information.
Yeah, is it obvious how these two are connected? Like I see this, the goal you're trying to solve, and then you have the Schrödinger like operator, but I don't see how really like one connects to the other. Maybe you said it and I missed it.
Yeah, so I honestly I don't know. I mean, we started with like the quadratic cost function, and then we solve it. There was absolutely no connection with Schrödinger, and then the connection actually becomes a little bit more clear when we pick the absolute value for the cost function. Then we saw the Schrödinger equation just appears everywhere.
Oh.
But intuitively, I cannot really give you any intuitive answer for that.
Okay, so maybe you're saying if you start at this, you start at the like optimization problem you set up, you do some algebra rearrangement, which you haven't shown us, which is fine, and you arrive at essentially a differential equation or whatever that looks like that.
Yeah. So I mean, because you're minimizing this integral, right? So the Fisher information is integral, and then you can just do some take the first derivative and second derivative. You just set the first derivative equal to 0, and then that equation actually gives you exactly this.
Okay, interesting.
Yeah, so it's just the product of minimizing the Fisher information. So I mean, on a technical level, the connection is not very hard, but intuitively, I don't know if there's any kind of clear intuition. So okay, so the main result is this: if theta satisfies something like this, so the expected value of the cost function with respect to this PDF is exactly equal to C. So we satisfy the utility constraint. Then the optimal distribution. So remember, PS star CC is the solution of this optimization, is actually equal to this function. And again, this y2 is the function is the eigenfunction of the Schrödinger operator corresponding to the smallest eigenvalue. Okay, so now let's just have So before example, just the takeaway is that if we want to solve the KL optimal privacy mechanism, if we want to characterize the optimal privacy mechanism in the large composition regime and a small sensitivity regime, all we have to do, we have to basically solve this optimization problem. Sorry, we have to solve this differential equation problem. Okay, so by solving this differential equation, we are basically solving this optimization problem. Okay, so on one hand, we have some optimization problem which might not be very, very simple to solve. And on the other hand, we have this differential equation which might be way, way easier, depending on the cost function that you have. Okay, so now let's just have some example. So now let's just pick, the quadratic cost. And then, so for this particular cost, the differential equation that we have to solve is something like this. And it's a very, very easy differential equation. We can solve it. And then kind of surprising, the optimal distribution is actually the Gaussian. Okay, and that's exactly why we have this convergence here. So when the cost, the C is big enough, when the sensitivity is small, the optimal is Gaussian. So Cactus and Gaussian, in this case, they are essentially the same. And that's why we have this thing here. So we have Cactus converging to Gaussian. Okay, so now let's just have a look at another example. So here the cost function is absolute value. Then the differential equation that we have to solve is something like this, which is very, very kind of well-known differential equation in statistical physics. And so people, for like 50 years, they have been dealing with this differential equation. And the solution of this differential equation is something like this. It involves, this function, which is called Airy function, and it's defined as this kind of integral, the limit of integral. Okay, so we call this density Airy density or Airy distribution, and the corresponding additive mechanism, we call it Airy mechanism.
Do you have a picture of what that looks like by any chance, or?
Perfect. Okay. Yes. So the Airy distribution is kind of between Laplace and Gaussian. So here, the tail of Laplace is like e to the minus x, but the tail of Airy is like e to the minus x 1.5. So it has a lighter tail than Laplace, but heavier tail than Gaussian. Okay, so now let's just have some numerical experiment. So we have an Airy mechanism, we have Cactus mechanism, and we want to compare a Cactus and Airy with Laplace and Gaussian. Okay, so this is the comparison of Cactus and Gaussian. So what we have here is this is the composition result using moments accountant and subsampling. We are basically using the TensorFlow privacy. So we just go to TensorFlow privacy, we get the moments accountant part, and then we use it to generate this to plot. Okay, so the x-axis is the number of composition, the y-axis is the privacy parameter epsilon. Okay, so here delta is 10 to minus 5, subsampling rate is something like 0.004. The quadratic cost, we pick the quadratic cost, and the utility constant is capital C is 0.1, and the sensitivity is 1. So what is important here is that if you look at, for example, 3000 as your composition. Okay, so Cactus gives you this epsilon, which is something like maybe 5. But Gaussian gives you something like 9 or close to 10. So you get a double epsilon for Gaussian. So there is a significant improvement from Cactus over Gaussian.
Do you know how the accuracy of these two compares after these compositions?
Very good question. Yeah, so this is actually the accuracy. So this is, again, the y-axis is the accuracy, and the x-axis is the privacy parameter. So the Cactus actually sits on top of Gaussian. So even the accuracy is better than. So privacy and accuracy both are better for Cactus. But I have to say that we know that moments accountant is not optimum. So right now, we are working on some kind of accountant kind of technique. And if we use, a better accounting technique than moments accountant, then I expect, the gap between Cactus and Gaussian is even better. So it's even bigger gap.
Right. Have you tried there's the best accountant that I know of right now is the one by Gopi and Watches.
Yeah, exactly. Yeah. So I think the issue is that, with all those FFT based, or even the Gopi paper, the issue is that, they assume the distribution of the privacy loss random variable. But for Cactus, it's not very easy to characterize, the distribution of privacy loss random variable. So what we need, we want to have an accountant technique which does not really require the full distribution of privacy loss random variable, maybe just the first moment or second moment.
I see. Sorry, let me see if I understand. So like in the analysis, like you can apply the Gopi et al. Paper to the Gaussian composition, but it won't be applicable to your composition.
Exactly right. Yes.
Okay, so it might not be a fair comparison. I see.
Yeah, absolutely. Yeah, right. Yeah. Sure. Great. Okay. So now Laplace. So this is actually the comparison between Airy and Laplace. So here on the x-axis we have the sensitivity, and then the y-axis is the maximal KL-divergence. And then we already know that Airy is going to be optimal for a small sensitivity. And so as you can see here, there is a gap between Airy and Laplace for a small sensitivity. So the smaller the sensitivity is, the better gap between Airy and Laplace. And then at some point, Airy is going to be is going to be worse than Laplace. So a small sensitivity for this problem is going to be 1.75. So for anything smaller than 1.75, Airy is better than Laplace. And then, so now let's just do another moments accountant. So here we have epsilon in terms of the number of composition. So now Airy is the orange one. So Airy is going to give you a better epsilon compared to Laplace, but the gap is not as big. So for example, if the number of composition is 4,000, Airy gives you something like maybe 0.6, and Laplace gives you 0.8. So not that much difference. So now let me
sure here. Like when you were deriving these things, you used a few approximations here and there, which is okay. But I'm just wondering if the like epsilons and stuff, and the epsilons and deltas you quote here are like guaranteed, or is there some approximation of that?
So yeah, so I guess definitely there are some approximation, because we use like the law of large number to say that the average, the sum of bunch of IID random variable converges to this mean. So that's the only approximation that we have. But for the quantization, the approximation is very, very negligible.
It's fair, I guess. Yeah, I don't know. I'm just a little bit cautious there, because I thought like, if you use Gaussian DP as accounting, then it gives you much better numbers than moments accountant. Like I've seen papers where they compare the two numbers, and it seems to be like quite a bit better. So I'm just a little bit hesitant to fully accept that. But maybe it's just a deficiency of our accounting techniques right now.
So hesitant about what? About this gap between Gaussian and Cactus?
Yeah, I guess like just earlier in the talk, you mentioned that like you're doing a CLT approximation, which may not perfectly capture what exactly composition is doing.
Absolutely, no, that I agree. That I agree. So so we haven't even done the CLT. All we did was basically the law of large numbers. So it was the first order approximation. So it was even like weaker than CLT. But yeah, absolutely. So that approximation is there. I mean, but if you look at the plot, I guess the plot should kind of, I don't know. I mean, it gives you all the. So given with all those approximation on the Cactus, gives you something way better. But this gap actually does not come for free. I mean, sampling from Cactus distribution is actually way harder than sampling from Gaussian. So let me be very, very clear. I mean, Cactus is not ready to be applied, in practice, because we don't know how to sample from Cactus. It looks very ugly. But on a paper, at least there's a significant gap.
Okay, cool.
So now let me wrap up, with some kind of future direction. As I mentioned several times, we need some better accounting technique for at least for Cactus distribution. So all the great accounting technique like FFT based accounting technique or convolution based accounting technique, they are not good enough for all mechanisms. For example, Laplace mechanism cannot really be taken care of using FFT, for example. Cactus cannot really be taken care of for almost any existing accounting technique. So what we are doing right now is basically just developing a better accounting technique that holds for any general mechanism. And then so the second question that we are looking at is that what do we mean by large composition regime? How large the composition should be in order to kind of switch to KL optimization? We still don't have any answer, but what we are doing right now is basically just going from the first order approximation to second order approximation. So instead of using the law of large number, we want to use the central limit theorem or a little bit more advanced kind of concentration result to kind of justify KL-divergence, and also maybe bring maybe not just the first moment, because if you remember, KL was the first moment of the privacy loss random variable, but maybe we need to bring the second order, the second moment of privacy loss random variable. Maybe we have to bring that into the optimization as well. So the paper and the codes are available. You can just go and download them. And then, so the code is also there. You can just play with the code if something is not 100% clear, or if you are still hesitant, you can just play with the code. Yeah, so thank you so much, and I'm happy to take any question if there is any.
Cool, yeah, thanks so much, Shahab. This is a great talk.
Thank you.
We'll open it up for questions from anyone. I have one or two, but I'll let anyone else go first.
I have one quick question. You mentioned it's unclear how to sample efficiently from the Cactus distribution. Do you know if there's any like Markov chain approach that might be useful for that? Or
I think even simpler than that. What we have done, we basically use a bunch of Gaussian distribution. We just look at the mixture of Gaussian distribution, and then approximate Cactus. So I think we use something like maybe 8 Gaussian to kind of approximate Cactus, and then we sample from the mixture of Gaussian. But the Markov chain, honestly, I haven't done anything. But I think that should be the next step.
Yeah. Thanks.
So I'm kind of curious about this small sensitivity regime. It's kind of a little bit counterintuitive to me because, for example, the Gaussian case, you can always just rescale it, and then that's like, you know, a smaller sensitivity. It's the exact same thing, really. Like somehow I don't generally picture the sensitivity to be really something that affects the mechanism. It'll just be a scaling of the mechanism. I'm just wondering, like, yeah, why does it make a difference here?
I honestly, I don't know. I guess again, on a technical level, that means, you know, Fisher information comes, you know, to the picture. That is a technical answer. But on a non-technical, I do not really see. I mean, so it was the product of just a curiosity. I mean, because, you know, that plot, you know, Cactus and Gaussian becomes the same. We wanted to analyze that. We wanted to understand, you know, that convergence. That's why, you know, we look at the response sensitivity. But beyond that, I don't have any other intuition for it.
Okay, sure. I feel like,
but again, I mean, there are a bunch of queries, you know, whose sensitivity are small. So you cannot really just, at least, you know, this analysis, you know, shows that if your sensitivity is small, then do not treat them exactly the same as, you know, sensitivity equal to 10, for example. There is a gap between a small sensitivity and big sensitivity.
okay. I feel like one perspective that I would personally think about like if I have time is, you know, what you did was you did a transformation fixing the value of C to be equal to 1, and then you put that into the sensitivity. I wonder if it's more, if another perspective that might be valuable is doing the other thing, like fixing the sensitivity to be 1 and then changing the sort of C value. And that would kind of be saying, like, then would be somehow a more versus a less accurate mechanism.
Absolutely, yeah, exactly. And so you can do that in the reverse direction. You can basically just fix, you know, the sensitivity to be equal to 1, and then just look at, you know, the C as S over C. So yeah, absolutely. So a small sensitivity means, you know, the accuracy is going to be a little bit worse.
Okay.
Sorry, a little bit, absolutely, a little bit worse. Yeah. Sure. So because C is going to be big, yeah.
Cool. Yeah, this was super cool. I don't think I personally have any other questions, but I've asked like all but one of the questions. So if there's anyone else who's got anything to ask. Cool. Anyway, it was great having you here virtually, and I'm sorry you couldn't make it in person. You know,
yeah.
Come here anytime in the future. Lunch.
Absolutely. Yes. Yeah. Thank you.
Some more folks here.
Absolutely. Yeah. Thank you so much for the invite.
Cool. Thanks for being here.
Okay.
All right.
Okay. Bye.
Thanks everyone for coming. See you.